I'm happy to introduce Professor Michel van Garrel from University of Birmingham, UK. So he's going to talk about Introduction to Tropical Geometry.
Oh.
Yeah, let's give him applause.
Well, thank you very much. It's nice to leave the UK to go to a place that has sunshine and warmth. Thank you very much for the opportunity to speak here. Thank you for organizing this wonderful workshop. I'm really looking forward to it. It is for me really every time really great pleasure to come to Korea, and I spent 3 years here. Those were extraordinary years, and it's really a delight to be able to give back something. All right, so I change my title every day. So today is going to be about tropical geometry, but the kind of overreaching, I want to say a few words about the overreaching goals of the lecture series. So maybe the title for the lecture series I settled on most recently is From Lattice Duality to Mirror Symmetry. So you can see this is mathematics, lattices, and this is physics. So I'm in line with the theme of the workshop. And let me give you a summary of what I hope to cover. So there will be broadly 3 themes, and we will advance in increasing levels of generality. And so theme 1 will be a duality between toric Fano varieties and toric Fano varieties. And this is going to be given by a, I don't know, reflexive polar duality, maybe. Or reflexive dual. Polar slash, so reflexive slash polar dual. I told you it's about tropical geometry, but there's also a bit of polar geometry. And what this duality is going to do is it's going to exchange 2 lattices. So we'll have here a co-character lattice. Is that okay for the back? Is that too small? Or is it okay? Okay, very good. So we'll have a co-character lattice N. We'll have a character lattice M. And so M is N dual. And then this duality is going to exchange them. So the co-character lattice becomes M, and the character lattice becomes N. Right. So that's going to be the first theme. The second theme is going to be about skew-symmetric cluster varieties. Which is really a generalization of theme number 1. And here we'll have on one side the A cluster variety. And on the other side, we'll have its dual X cluster variety. And on one side, we'll locally have some lattice N. On the other side, we'll locally have some lattice M. So what I want to say is that this duality is going to also get interchanged. So this the same interchange of lattices. And then the final theme will be Fano varieties, which are going to be what we call mirror to polarized cluster varieties. So this is somehow a broad overview, and maybe we'll mention. So the goal is to get like one application, or I don't know, one result. So physicsy result, which is going to be a quantum period. I mean, if it has the word quantum in it, it must be physics, right? Quantum period of Fano. I mean, maybe you call this y, and maybe you call this x. There's a little parameter. Quantum period of Fano equals classical period of xt. Okay, so this is somehow what I hope to be able to cover. Any questions so far? Okay, and then I was absolutely. I was good point. So there is what is presently called a guided discussion session, and so we will do. This is on Wednesday afternoon, and we'll do something. And exactly what we do will depend on how far I get until Wednesday. It could be a kind of doing an example in detail, doing some examples in detail, doing some exercises, or it could be something also rather interactive. So I think maybe I'll postpone exactly what's going to happen to just like allow for some freedom depending on how fast I progress. So we thought about different ways we could do this, but yeah, we'll decide later. Okay, so I know many of you are PhD students, and not many of you are algebraic geometers. Maybe not very many of you at all. So I'm going to start with a crash course in algebraic geometry. Yeah. So crash course. What did I call it? In algebraic geometry? And maybe I'll say just a few words of intuition. So we have spaces which are given by polynomial equations. we have functions which are polynomial functions. Functions or rational, which means ratios of polynomials. And then I will add an extra bit, which is related to logarithmic and tropical geometry, which is that we want to keep track of boundary. So maybe, so what does boundary mean? It means divisor. I mean, it means SNC divisor. And I'll say what that means. Okay. So those are three things to keep in mind as I give you this crash course. Also, I'm not going to be the most rigorous. I just want to get through it. Yeah. All right. So for us, an affine variety will just be, so an affine variety is going to be a subset of Cn given by polynomial equations. Where the fi's are irreducible polynomials, so we take some irreducible polynomials, we look at the solution set. Then its coordinate ring is maybe so we take the ring of polynomials and we quotient out by the ideal generated by the polynomials. Okay? And so we can think about CV or the polynomial functions so a polynomial function on V is given by a polynomial, but it's subject to this relationship because so because it has to be defined on the I mean these vanish on the variety. So if you have a polynomial function and you were adding some multiples of this, it still gives you the same polynomial function. So you have to take the quotient. Okay? And now, so I'll say something about what topology we're working with, and then how to build more general varieties. So definition, the Zariski topology. So for this, the closed sets are given by subvarieties. So meaning if you have a variety, a subvariety will be given by intersecting with more irreducible polynomials. We have some distinguished opens. So the complements of the closed sets are the open sets, and we have some distinguished open sets. Which we're gonna, so if you choose an F in the ring of functions, coordinate ring of functions, ring of functions. So if you choose a function, a non-zero function, then you can look at the open where the function is non-zero. It's the set where f is non-zero. And you have the functions on it, which are the following. So functions, algebraic functions, has functions. So we start with the, maybe let me write it like this. So this is an element in CV, where we take the field of fractions. So you can see that we allow, so we allow to invert f to arbitrary powers. Okay? And now this is enough to define what varieties are, because a variety is going to be built by gluing together pieces like this. I mean, a variety is a ringed space is X, O of X, where X is a space, O of X is a sheaf of functions. I mean, it's a sheaf of rings, but in this case, it's going to be a sheaf of functions. And then the condition is obtained by gluing together things as above. Gluing together. Fine. So V is an affine variety as we defined it. By the way, this is an affine variety. How do you obtain it? Well, you can embed it in a bigger affine space, and then the equation f non equals 0 becomes the equation that f times a generator is equal to 1 of the extra direction. And then I didn't tell you what this sheaf of functions was. But you can kind of piece it together. Because here I told you what it is on one of these distinguished opens, and then you can, I don't know, you can intersect opens, etc., and get your ring of your sheaf of functions. So it's really, if you choose an open for your variety, then or for your affine variety, it'll be given by polynomial functions. Sorry, ratios of polynomial functions such that the thing at the bottom doesn't vanish on your open. Okay? Questions? So now we've seen what is the space, we've seen what are the functions, and now we need to talk about the boundary. So maybe just, if you were doing maybe algebraic geometry before the 50s, or maybe end of 19th century, early 20th century, you'd be really interested in this space. And then in the 50s, 60s, especially due to the work of Grothendieck, he really emphasized that we need to look at functions on the space is more important than the space, yeah? So that's this bit. And now maybe in recent years, I don't know, I'm not a specialist, but we understand that we should really also keep track of a boundary, which is what I'm going to tell you about now. And I'm a little bit sloppy with my definitions because the point is to get forward, right? So a divisor on X, or on X, which I mean, this is X and its sheaf of functions. So is an element of the set of elements given by some AI di, where di is a subvariety and AI are some integers. So kind of very, very simple construction. And this is, or maybe I want to call this div X. So divisors on X, or divisors on X, yeah. We say that a divisor, okay, so that's great. And now we want to choose some particularly nice divisors. And there will be divisors which are normal crossing. So D equal D1 plus DL. So here, AI are equal to 1. So I just take a finite sum of them. This is normal crossing. If locally, so there's a word here which I'm not going to talk about, but you would have to put eta locally. But I just this means I'm not going to talk about what this means. But so we're going to say locally, D is given by something like x1 times xp or xr, I don't know, r equals 0. So these are local coordinates. Yeah. So at every, let me give you an example. I think the example is going to illustrate. Okay, let me finish the definition. This is for normal crossings. Oops. This is normal crossing, and then simple normal crossing, simple normal crossing killing the simple normal crossing if each di is smooth. So I didn't tell you what smooth means. You can think about the defining, you take the defining equations and then you take all the partial derivatives and, then like not all of them vanish everywhere. That's good enough. So example. Sorry, I'm so we start with the projective plane. We have, it has an x-axis, it has a y-axis, and then it has a z-axis, which is the line at infinity. Here, and so locally we have and this is 0, 0, and then 1, 0, 0, 1. Yeah. And so you can see that so a local equation here is x, y equals 0, right? This is x equals 0, and this is y equals 0. Yeah. Maybe locally here, the equation is y equals 0, and yeah, and then maybe I can also say what happens up here. Maybe. So here we have local coordinates, z1, which is 1 over y, z2, which is x over y. So yeah. Anyways, and then we also have, again, we have local equations, which are z1 times z2 equals 0 for the boundary. And similarly, at the bottom, here we have local coordinates. U equals 1 over x, and that's this one, and v equals y over x, and then again uv equals 0 are local equations. This is local equation for D. So this is D is the sum of those. Questions? And this is an SNC divisor in that example. So this is an SNC divisor. All right. So we're not done yet. but you can see, you can you can see in this example, here we kind of decompose P2. We said there's like an inside C star squared. That's kind of the interior. And then there's the boundary. This is the boundary. And we can also see that there are boundary strata, right? So this is, here we have a deep strata. This is boundary strata of codimension 1, and then here boundary strata of codimension 2. Okay? Okay, you're all dying to know something about tropicalization, so let's get there. So we're going to start with divisors supported on D of X. So here X, now X is again, so we have X, variety, and then D is an SNC divisor, simple normal crossing. So we write D equal D1 plus DL. Then we can look at divisors supported on D. So if you remember this definition, here I could allow my DI to be any subvariety, but when we require it to be supported on D, so this means supported on D, on D, then that means that the only divisors we allow is sum of AI DI for those D. I mean, here I wrote it, maybe I shouldn't have written it, maybe I should. Anyways, so here I could have any subvariety, right? But here, when I write this, when I require it to be supported on D, then I ask these sums to be AI times DI for, DI inside D. Yeah. Right, so this one is well, okay, I really should change the notation because so let's call this one here YI. And subvarieties, and then here, yeah, perfect. So this is going to be sum AI DI. I mean, here I is from 1 to L, where AI are elements in Z. I can make it into a vector space by tensoring with R. So I tensor with R. Oops. So what does it mean? It means maybe I can write it like this. So tensor with R. So now it means I allow this to be inside R. I allow the coefficients to be real. And finally, I can take the dual. So we mark so this is a vector space. So it's a vector space that contains a lattice. And now this is the dual vector space. And by general facts about vector spaces, this has a dual basis. And That's right. Oh yeah, thank you. Good point. Thank you. And same thing here. If we choose them to be integers, we also get some lattice. I mean, maybe I can just write it as we have this sum of z di dual sits inside as a lattice. Div dx. All right. Questions? And yeah. So we're yeah. So this is we're studying. Well, we're studying the boundary, and now we're gonna like define what its tropicalization. So if we take a subset I, which is 1 to L, we define di or xi. I don't know which one's a better notation, but I'm just using both because I might confuse it or like exchange it otherwise. And then for I, so we take a subset of indices and then we intersect them, intersection of them, yeah. So here we would have either each of the components or the intersections or the empty set if you were to intersect all of them. So for EI such that xi is non-empty, so we define sigma I to be sigma I to be the cone generated by the di dual. So I take the R non-negative span of the di's. So I don't know if you prefer, I can write it as sum. Well, this is fine. Right? So I just take, yeah. I look at the elements di dual inside here, and I take the non-negative span of them. It also has integer vectors. Let me draw it like this. Z non-negative. This is integer vectors. So the top is a combination of those where the AIs are non-negative real numbers. This one we take, yeah. And then we take those cones. And now the tropicalization of X is the union of these cones. Maybe this is all part of a big definition. So the way I'm gonna do it is I'm gonna or x meaning xd. So sometimes I'm from now on, sometimes I write x, sometimes I write xd. But I always have this choice of simple normal crossings divisor that I carry with me. So here variety and SNC divisor. Right. So I really carry this with me throughout. And so this is going to be given. So this is called sigma of x is the union of these fans. Sorry, the union of these cones. Provided that xi is non-empty. And this is called a polyhedral cone complex. This is a So what is a polyhedral cone complex? So it is a set of cones with the property that every face of the cone is part of the set, and every intersection of cones is part of the set. Let's look at our example of P2. So we have three divisors. Maybe I can, yeah, so it's the same picture we had. This is the picture, right? And so we have to look at these cones sigma I, such that the intersection is non-zero. So for this to be two-dimensional, for sigma I to be two-dimensional, I need two generators. And that happens. So for example, okay, let me draw all the cones. First, well, we have a cone, which is, of course, the following. This is, let's call it dx. This is sigma x. This is the cone generated by dx dual. We have another one, which is generated by dy dual. This is sigma y. So I just use that notation. You can guess what I mean. There's one which is generated by dz dual. This is sigma z. So those are the one-dimensional ones. In order to get two-dimensional ones, I need to take two of them, but subject to the condition that the intersection is non-empty. Well, here, this point here is, for example, is the intersection of dx and dy. That's non-empty. So we get a cone for this. So this is the cone sigma xy, and it also has these lattice point generators. So it's a two-dimensional cone, and with these lattice points. And similarly, x and z, dx and dz have a point of intersection. So that gives me something here. So dx, dz, this gives us sigma xz. also a two-dimensional cone. And finally, the last one. Which is sigma yz. But of course, now we need to glue them together, because I mean, I told you polyhedral cone complex, there's a condition that, well, the face of one should be another element of the set of cones. So we're gonna, we're gonna glue them. So glue, maybe I use white, glue, 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 glue. Here. And now an important point is that if you glue them together, you lie inside this thing, This is inside div d p2 real dual, and so this is isomorphic to R3. Yeah? So it's, it's definitely not equal, but it's yeah. So really, there's a three-dimensional space, and then we're looking at the positive quadrant inside R3, and at the I don't know, the hyperplanes, the quadrants of the positive hyperplane. Like so, we this one, this one, this one inside R3. One more time, please. Yeah. So okay, yes. So I could also So okay, you're saying I should also add sigma empty set. Yeah, that's absolutely yeah. So I did absolutely. So there's one more cone, which is the empty set, where the intersection of I in the empty set, di we define to be x minus d. So kind of the empty intersection. So there's also a cone corresponding to that. So maybe we also want to glue that. Yes. Here. Okay, sure, yeah. Absolutely. Thank you. More comments, questions, suggestions? Yes? What's your background? Because it depends. Are you? So there's different answers. That can be answered in many different ways. And so maybe if you tell me your background, I can try like mathematical background. Would you say? Okay, okay. So one way. So maybe the way we want to think of the reason we want to take the dual is because it's something that's going to intersect. It's going to pair with divisors. Yeah. So if you're an algebraic geometer, you can think of them as being valuations. They give you valuations. And so it's something that you're able to pair with a divisor. So something that pairs with a divisor is a dual, right? Yeah. So maybe if in toric geometry, which is what we're going to do later, it's they're going to correspond to co-characters. Yeah. But anyways, so maybe the best answer. This is an excellent question, and the best answer is, well, we're going to pair with it, and there's going to be a geometric meaning, and the geometric meaning is going to be our divisor is something in codimension 1, and then we're going to have some curves. So these lattice points will determine some curves, and the curves. So this is this is going to be an element of the lattice. Well, there'll be some curve, and then the curves will have some intersections with the divisors. So it's really duality. I mean, duality in the sense of linear algebra, pairing of vector of a vector and dual vectors. So yeah, it's a good question. It's a good question. But you're right that it's yeah. Or maybe another way to say it is you can see that this is inclusion reversing, right? So if you go deeper in the strata of the boundary, this becomes larger. So it's kind of the dual picture. Yeah. I don't know, dual intersection is dual to spanning, at least in this language. Yeah, excellent question. More questions? Comments? All right, so maybe I do want to briefly introduce toric varieties, because I think yeah. And then we'll see how this is an example from toric varieties. So I'll just leave these two boards. So toric varieties. So here, so definition. So X is a variety. So we're going to assume, actually, we assume projective / compact / proper, whichever you prefer. Yeah, I mean, so we don't need to assume this, but anyways, we will in practice do as if. So we have a variety. But it also has a dense torus. So it has an open inside, which is C star to the n, and which is necessarily dense because in the Zariski topology, for a variety, the way we defined it, opens are dense. So dense torus. So yeah. And then the action of C star n on itself extends to an action of C star n on X. Okay, those are the conditions. So it has, a toric variety has different structures. It has the structure of a variety, in particular with its sheaf of functions. Then it contains this open torus, this dense open torus. There is and in such a way that the action of the torus extends to an action to X. So it means, so X has a, this is a, so X is a group variety. There's a group acting on it. Or, I mean, it admits the action, Well, anyways, C star to the n acts on X. So there's some immediate consequences to this, which is that this implies that the complement stratifies as a union of di with it's a closure, each di is a closure of n-1 dimensional orbit. If you have a group acting on a space, you can decompose the space in the orbits. And then in this particular case, if you take the codimension 1 orbits, and then the closure, you get the complement of C star to the n. And let me give you a definition, and then we'll end. So definition so a co-character is eta C star to C star to the n. We have a lattice of co-characters, and you can, this is, this is inside, we think about inside X. Then we're lattice of co-character. N, which is the set of, so it turns out you can write them as NN, that's a great notation. So it sends S in C star to S to the N1, all the way to S to the Nn in C star to the N. And then the decomposition, or the, I don't know, yeah, so D, we get a decomposition of NR, which is N tensor R, or the integer. So this is isomorphic to Zn, by the way. So decomposition, which is sigma x of this into cones, and then we'll, you can think about this, or we'll start with this next time, which is that sigma x equal tropicalization plus global embedding into NR. So I explained to you what the tropicalization of this thing was, right? Sigma of this. So it was this polyhedral cone complex inside Rn. And now we will see at the start next time that these co-characters determine a decomposition of this vector space into cones. And then I will explain that this is the same decomposition as we have this one, but with one additional property, which is that there's a global embedding in this lattice in N, and because when you look at this picture, we have this element, and I'm gluing this element to here, yeah. But it's like, I'm not telling you that maybe this element should go somewhere else. I'm not telling you how to map this element to the other side, right? So I'm not telling you, so no info about how to map tangent vectors across cones. Right, so if I have here a little tangent vector, I can't tell you where it goes on this side. I can tell you where this one goes because it's identified, yeah, and then I can kind of parallel transport it, but not the other ones. Whereas here, this really tells me, tells us how to identify tangent vectors. So anyways, you can think about this. It's a fun thing to think about, and then we'll start with this next time.